Hello and welcome to Honors Function. In this lesson, we're going to go over the limit notation that was introduced with the end behavior of a polynomial. Now, a limit does not necessarily describe an end behavior, so this is why we need to extend the notation. Let's begin. Let's look at a function that is not defined at a. There is a hole there. So the function is not defined at a, therefore the function is not a polynomial. A polynomial is defined over the set of real number. And let's see where are the output of this function as the input approach a. So I want to look at the limit of f of x as x approaches a. There are two ways of approaching a. You can approach a from the left of a or from the right of a. Okay, so I'm going to take a few value right here, getting closer and closer to a from the left, and same thing on the right, closer and closer from the right. So let's look at this one. Where are the output? Where is the output of this input? It's right here. Let's look at this one. It's going to be right here. This one is here, and finally this one, pretty close to a, is here, right here. Okay, now let's go from the right. Output here, output here, output here, and when I go even a little bit closer, the output is here. So when I went from the right, the output went this way. From the left, the output went this way. In any case, I see that the outputs are approaching this value right here. Oh, my Y line went off. This is what happened when I draw too many times on the same line. Okay, and I was saying they seem to be approaching a limit value right here, and this limit value is the limit value of this hole, the Y value of this hole right there, right? If I call this L right here, I will say that the limit of f of x as x approaches a is L. Now, it has to be approaching L from the left, okay? The left where I am right here, okay? I'm going down. And also from the right, okay? In both cases, I'm going towards the same value L, and that's why I will have a limit at a, because from the left or from the right, I do have a limit. We say that the limit of f of x as x approaches a from the left, there's a minus sign here from the left, okay? This means a from the left. This right here would be x approaches a from the left, and this one would be x approaches a from the right, is equal to the limit of f of x as x approaches a from the right, okay? And because I have an equality right here, this limit, the limit at a exists, and I will say it's equal to L, okay? So I write that when both limits exist and are equal. They have to exist and they have to be equal, all right? Okay, so this is what we mean by the limit of a function at an input. Now, of course, if your function is defined, so let me take a function that is defined at a, right here, I'll take a right here. Now, this function is defined at a, right? So if you approach a from the left or a from the right, well, your values, where are they going to go towards? They're going to be moving towards a very specific value, and we know what that is, right? Here, I'll just do this one right here. What is that specific value? This specific value is going to be f of a, okay? So when the function is defined, then the limit of f of x as x approaches a is just f of a. This actually is a definition of a continuous function at a, okay? Let's go over the first series of example. Okay, so in example 1, I'm looking at two limits, one at -1 and the other one at 2, of a function that is a polynomial. Now, a polynomial is defined everywhere. Therefore, I'll do the limit at -1. Please do the limit at 2, but this is super easy. The limit of f of x as x approaches -1 is, well, if the function is defined, it's just f of negative 1. And f of negative 1 is negative 1 cubed is negative 1 times 2 negative 2 minus negative 1 squared, so minus 1. So negative 2 minus 1 negative 3, negative 3 minus 1 negative 4, negative 4 minus 4 negative 8. Please do the same at negative 2. Okay, let's check out what's going on right here. I want the limit of f of x at 1. Okay, well, that's gonna be okay because the function is defined at 1, right? So the limit of f of x as x approaches 1 is what? Well, it should be f of 1. There's no problem of definition, right? So it should be 1 squared minus 1 minus 2 divided by 1 plus 1. So what do we have? 1 squared, 1 minus 1, 0, negative 2 divided, so it should be negative 2/3. Now, what do we do about this limit right here, the second one, at negative 1? The function is not defined at negative 1, so where will the limit be? So I'm asking you to check in your calculator with a table the value of the output as x approaches negative 1. So let's take the calculator and let's see how that works. So I have entered the function into y1 and I want to check the table, the limit at negative 1 of this function. So how do we do that? Well, we need to come near negative 1, right? So we want to do a table set. And we want the table start to be, let's say, negative 1. Now, I know it's not going to be defined at negative 1, but my delta table, I need it pretty small, okay? Because I want to approach negative 1 from the left and from the right, but with some small step. So let me try 0.01. And if it's too large, we'll go smaller. Right here, I want auto. I want the auto. I just want to check out my table. So let's look at the table right now. Alright, so of course at negative 1 you have an error because the function is not defined. But let's see what's going on before negative 1. So let's go, you are approaching negative 1 right now from the left, right? So, okay, now look at this. Look at these values. If I approach negative 1 from the left, see these are pretty small value around negative 1, right? Very, very close to negative 1. As my x's cluster around negative 1, from the left, the y's seem to be clustering around what? Around negative 3, right? Negative 3.09, 0.08, 0.07, 0.01. Right? Let's check out if it's the same from the right. So I'm gonna go from the right right now and let's see. Yeah, look at this value. Negative 2.95, 98, 99 right here, right? So I will say that the limit is negative 3. Okay, the limit at negative 1 seems to exist because both limits from the left and from the right, they both exist and they are equal. Okay, so I do have a limit at negative 1 right here, and it's seemed to be negative 3. Now we checked it with a table. Is there another way not to use the table? Well, let's notice something. I want you to check out something. Look at the function I'm giving you, f of x. F of x is x squared minus x minus 2 over x plus 1. What happens if you simplify this fraction? You got x minus 2 times x plus 1 over x plus 1, okay? And this is just x minus 2. And this function is defined at negative 1. What did you just do right here? You just removed the only value where the function was not defined. But we have a theorem in math that says that the limit of x squared minus x minus 2 over x plus 1 as x approaches negative 1 is going to be exactly the same as the limit of another function that is equal to this one, except maybe at 1 or 2 value or even 10 values. Okay, if you just remove a certain number of values, you're going to have the same limit everywhere. So it's going to be equal to the limit of x minus 2 as x approaches negative 1. And here, this function being defined, I'll just plug in, substitute, right? Negative 1 minus 2, and that is negative 3. You see? What we saw with a table, now we just did it algebraically. So this is one technique to find the limit of a function. If you simplify the function and you remove one value or even two value or a finite number of values, then the limit will be the same. Please do example number 2 and example number 3. Let's now go over another limit notation. So in this case, I'm going to be looking at the limit of a function that has a vertical asymptote at a. Okay, so how do we write this? Again, we need to approach a from the left and from the right. Right here from the left and from the right. So let's check out where the outputs of the functions are as the inputs are approaching a from the left. So here's the first one right here, first output, second output, third output. Okay, let's go a little bit closer now. Right here, and okay, well, let's go. I'm almost out the screen right here, right? It's pretty high. So let's do the same on the right. Here's the first one, here's the second, and if we go closer and closer and closer, you see you're gonna have to go really far out to find the output, right? So what does that tell you about the limit? The limit in this case is going to be positive infinity for both the left and the right. Okay, so I should say the limit of f of x as x approaches a from the left is positive infinity, and also from the right. Okay, it doesn't have to be positive infinity on both sides. Here's another case. What about now if we're dealing, here's the vertical asymptotes, and here is a function this way like that, and then on this side it would go down, right? And this is still a. What's going on if you approach a from the left? Well, the limit of f of x as x approaches a from the left is positive infinity. But where are you from the right? We're from the right. See, positive infinity from the left right here, right? But from the right, you dive down. From the right, it is not positive infinity, it is negative infinity. Okay, so here is another notation for the limit, and it describes a vertical asymptote. So writing this or writing that the graph has a vertical asymptote at x equals a is the same thing. It's two ways of expressing the same vertical asymptote. Okay, now let's check out a horizontal asymptote, and that's going to be the last limit notation we are going to cover today. So here is, for example, the presence of a horizontal asymptote to the function. So this is another case where we're going back to an end behavior, right? This is going to be an end behavior, but contrarily to polynomial, the result is not going to be plus or minus infinity. Here we will write that the limit of f of x as x approaches plus infinity, so we have seen this limit before, right? But now the output is going to be L. All the output of the function as x grows very large, let's take this one, this one, this one, all the output of the function are going to be coming close to L, right? They're going to all be moving closer and closer to this limiting value right here, L. All right? Okay, let's go over some examples now. Okay, so I'm asking you to graph this function. We use a calculator for that, to determine the equation of the vertical asymptote and the equation of the horizontal asymptote. Express both sets of equations using the limit notation. Okay, so let's check out the vertical asymptotes. I have already entered the function into y1. Let's look at the graph. Here is the graph of the function. I see two vertical asymptote, one at -1 and the other one at 1. And I also see a horizontal asymptote that seems to be the x-axis, right? 0. Okay, now at -1, you see if you go from the left, it goes to plus infinity. But from the right, if you approach -1 from the right, it's negative infinity. And the other way around at 1. So let's express that. So the limit of f of x as x approaches -1 from the left is plus infinity, and the limit of f of x as x approaches -1 from the right is negative infinity. That means vertical asymptotes at x equals -1, and also the limit of f of x as x approaches 1 from the left is negative infinity, and the limit of f of x as x approaches 1 from the right is positive infinity, and that means a vertical asymptote at 1. We also have the horizontal asymptote, that is just the x-axis. So in this case, we can write that the limit of f of x as x approaches either plus or minus infinity, in both cases, it's going to be 0. Now, we're going to have to be careful. It's not always going to be the same at plus or minus infinity, okay? All right, please do example number 6, and let me finish this lecture with a result that you have to know. All right, let's look at this function, f of x equals 1 over x. We call this the reciprocal function, okay? The reciprocal function. The reciprocal function is not defined at 0. It has a vertical asymptote, and the limit of f of x as x approaches 0 from the right is positive infinity, while the limit of f of x as x approaches 0 from the left is negative infinity, okay? If you take x to be very, very small but positive, for example, 10 to the negative 5, and then the next one, so that's going to be x1, and the next one is going to be 10 to the negative 10, and then the next one is going to be 10 to the negative 20. You see, these are really, really, really small values that are approaching 0, right? What is the reciprocal of this value? What is 1 over x1? 1 over x1 is 10 to the 5. 1 over x2 is 10 to the 10. 1 over x3 right here is 10 to the 20. These reciprocal are getting very, very large, okay? So the reciprocal of something very small is something very large. This is what I want you to remember. And also right here, we could increase the power, okay? So what happened, for example, if you have a power 3? Well, the cubic function is going to come closer and faster towards 0. It's going to be the same thing that we kind of notice with polynomial when you increase the power, right? It's going to be right here. It's going to be closer to the x and y axis, flatter, I guess. And if you increase the power one more time and you go to 5, it's going to be odd, okay? Then it's even going to come closer and closer to 0, okay? Like that. So this rule, this limit rule, actually is true when you take 1 over xn, okay, for n odd. What happens if n is even? Well, let's take a quick look at it. Well, if n is 2, for example, 1 over x squared, then the output cannot be negative, right? So this branch that was here when n was odd is going to be flipped because no output can be negative, and we're going to find it right here. So in this case, the limit of f of x as x approaches 0, I don't need to say 0 from the left or from the right, because from both sides the limit is plus infinity. What happens if you increase the power, right? If you go to 4, well, the same thing. You're going to be closer and closer to the y-axis. So it's going to go faster and faster towards plus infinity, and therefore the result is true for n even in this case, right? N even. All right, let's finish with a couple of examples, and we'll be done with this extension of the limit notation video. All right, so we have to determine the transformations of the graph of the reciprocal function to the graph of the function below, determine their vertical asymptotes and horizontal asymptotes. So we want to see how the reciprocal function gets shifted to this function given, x minus 5 over x plus 1. How do we do it? How does that happen? Well, this is actually not difficult. Let me show you how it works. You take this function right here, x minus 5 over x plus 1, and you find a way to write the denominator at the numerator. So my denominator is x plus 1, so this x, I'm going to turn it into an x plus 1, like that, right here. I'm turning this x into an x plus 1, but because I don't want to change my denominator, this plus 1 I subtracted right away. That's minus 1, okay, so that's just x basically, and then minus 5. And I don't change my denominator, of course, x plus 1. So why do we do that? Because this is x plus 1 minus 6 over x plus 1. And now you can break this into two fraction, x plus 1 over x plus 1 minus 6 over x plus 1, which is 1 minus 6 over x plus 1. That's it. Let me show you what happened if you had a coefficient in front of x. Suppose you have a 3 right here. Okay, so suppose you have a 3 right here. Well, what do? You would do the same thing. You would replace x by x plus 1, but this time you wouldn't subtract 1 because you've added 3, so you would subtract 3, and you would get a minus 8 right here, right, with a 3. And here you would have 3 over 3 times x plus 1 over x plus 1. That would be just 3. All right, so if you have a coefficient, you just kind of do the same thing. It's not a big deal. All right, let me erase that. And let's go back to our problem. Here we go. Okay, so now let's finish it. I do have now my graph shifting. I can write my graph shifting. This is what I want. So what do? I'm going from y equals 1 over x. What is my vertical asymptote of this one? Vertical asymptote is x equals 0. What is my horizontal asymptotes? My horizontal asymptote is y equals 0, right? This is just a reciprocal function. So what do? What is the first thing that you do? First thing that you do, you remember, you do a horizontal translation. Y equals 1 over x plus 1. Are you shifting the horizontal asymptotes? No, the horizontal asymptotes, y equals 0, stays the same. But this is going to get shifted. This is a vertical asymptote, so it's going to get shifted. Where does it go? It moves 1 to the left, right? So it is x equals negative 1. That's it. Then what's your next move? You go to y equals 6 times x plus 1. Now, if you remember what that does, it's a vertical stretch. You will not change the vertical asymptotes, right? It's just going to be the same vertical shift right here. Then you go to negative 6, so that's a reflection across the x-axis. Y equals negative 6 over x plus 1. These two transformations do not affect the horizontal asymptotes, right? The fact that you are, look, here was my x plus 1, so around negative 1 right here. What happened when you multiply by 6? So it's just gonna stretch it, right? But it's still, right here is gonna go a little bit slower towards the x-axis, but you're still gonna approach the x-axis. You still have that asymptote, right? And here, once you're gonna flip it, then you still have the same horizontal asymptote. It just gets flipped on the other side, right? But the horizontal asymptote doesn't change. So these two moves do not affect the horizontal asymptote. And finally, what do? Finally, you add 1. Now this will affect the horizontal asymptotes because now you go up 1. And if you go up 1, your horizontal asymptote is going to be y equals 1. Okay, so this is one way to get the horizontal and vertical asymptotes. With the next lesson, we're going to see a much more systematic way to look at that. Okay, but right now we're just doing graph shifting. Let's now go over the last example. Please do number 8 on your own, and I'm going to do number 9. Okay, here's number 9. I want the limit at plus or minus infinity. So we're going to first study at plus infinity, and then we'll study the limit at negative infinity. So this is the end behavior of this function. We're going to study that systematically in the next lesson. This is a ratio of two polynomials. It's called a rational function. Now we know the end behavior of a polynomial, right? It acts as is monomial of highest degree. So the top is going to be acting like negative x cubed. So if you take the limit at plus infinity, it's the same as the limit of negative x cubed, right? This is negligible, and this is negligible when you look at the limit at plus or minus infinity. So it's the same as the limit as x approaches plus infinity of negative x cubed over 3x5. Now what is this? This is the limit as x approaches infinity of negative 1 over 3x2. Okay, basically, or if you want, here let me write that differently, it's a limit of negative 1/3 times 1 over x squared as x approaches plus infinity. So what's going on at plus infinity right here? As x approaches plus infinity, x squared is going to get very, very large, but 1 over x squared will get very, very small. It's going to be 0, right? 0 positive because it's x squared. So it's going to be 0, but a 0 that is positive. And then you multiply this 0 positive by negative 1 over x cubed. So you just multiply by something negative. So anyway, it's going to be 0 no matter what, right? And at negative infinity, it would be exactly the same thing, right? You would do the same thing. So it would be the limit as x approaches negative infinity of negative 1 over 3 x squared. X squared gets very, very large positive. 1 over x squared is going towards 0, right? And you multiply that by negative 1/3, it's still going to be 0. So the limit at plus or minus infinity of this function is 0, right? So if you think about it graphically, I said 0, I said what kind of 0? 0 minus, right? Because this is a 0 plus, but then you multiply by something negative. So 0 minus means from below. So I don't know where the graph is here, all right? But I know as x approaches plus or minus infinity, the function is going to approach 0 from below the axis. Something like this, okay? From below the axis. Again, I have no idea where the function is in the middle. I'm just looking at this and this. Okay, this video is a little bit on the long side. Very important concept of limit. Thank you for watching.